Hey, Cassie, are you able to hear me?
Yeah, I can hear you.
Perfect. I can hear you too. And you can see my screen as well?
Yep, you're good.
Awesome. Okay. I'm gonna give it till 3:26. I'll start to extra grace. Okay, it's 3:26. We made it. So I just want to go through homework questions 1 and 2, which are actually pretty straightforward, I think, in the scheme of things. You guys have looked at them. So the first one says, consider a plane wave propagating in air whose pressure in pascals is a function of space and time given by this equation. So before we get into answering these questions, I wanted to take just a second to talk about representing complex exponentials or representing sinusoids with complex exponentials, because it's like this thing that's like everywhere, right? And we know, I mean, I think like everybody knows, like it works, right? Clearly it works. Like a lot of material is built up on the fact that you can do this, right? But I'm a big proponent of developing intuition, especially about stuff that's complicated. So I built a little animation around this, and maybe it'll, I don't know, be useful in some way if you guys look at it. So I'm going to jump over to Matlab for a sec. And I think this is actually the only thing we're doing in Matlab today, because, you know, I mean, you can do some of this other stuff in Matlab, and I would, in fact, even suggest it, but you don't need to, so we probably won't go over it together. Okay, so let's just run this. This pops up. So I don't think I can make that any bigger, unfortunately. If I drag that out, it's not going to get any bigger. So what you're looking at, as much as you can see it, is this part right here is this entire equation. Pressure equals 0.7 e to the 1000 t times or minus 5.83 times x. So this is just in the complex plane, right? And we're incrementing t. And what that looks like is a vector that's sitting there. And you guys have seen this, and you may have even seen an animation of it, but I wanted to show you kind of all three together. So let me tell you what the other things are real quick, and then I'm going to run it again. So this is the whole thing. This is in the complex plane. It's just whatever that is equal to in the complex plane at that time up there. On this one, I've fixed the position at 0 meters, but it doesn't super matter where we are. And we'll talk about what would change if we looked at a different position. But this is at x equals 0. This is the real part of that. So this is the projection of this thing, this vector, on the real axis, right? And then if we take that projection and we plot it against time, so just what is the sort of length of this vector over time, then we get this nice sinusoid, which is what's happening in real life and what makes sound, right? So that's just like graphically how you get from one to the other. So let me run that again, and we'll see how she looks. So that's the projection over here on the real axis. And this is just this flipped around over time. And that's how you can get from these complex exponentials to something that's sinusoidal and really physically happening. So what's the point though, right? Like, because I could do this, I could use Euler's relation and I could turn this into, and I could take the real part of it and I could turn that just into a cosine, right? Still give me that, wouldn't it? And that's kind of the point. Why do you do it? Why bother with a complex exponential? You guys think? Just to be mysterious, complicated, right? Because what? The wave is moving. So yeah, I mean, it definitely gives us this same sort of like rotational kind of behavior that we need, right? But I can do that with a cosine, can't I? So why the exponential? What's the point? What are properties of exponentials like that make them kind of nice sometimes?
Multiples of them, you can just add them on the power side.
It's mega easier to do math with them in a lot of cases, right? Taking derivatives and integrals and multiplying them together, it all becomes like so much simpler than doing it with the cosines and the sines, right? And that's really a lot of what it's about, right? It's just a mathematical tool, means the same thing, but is when you're doing complicated math, it's easier to do, right? So anyways, I hope that's somewhat helpful, because at least for me, I feel like that's such a mysterious kind of deal. Oh, so two questions I want to ask you guys, see if this sort of makes sense. If this is at x equals 0, how would these pictures change at some different position? Like say I just chose x equals 1, right? What does that do to this and to this kind of specifically? Let's think that one. Yeah, what is that? What do you call that when we're talking about? It's a shift, right? It's a phase shift, right? This is just gonna, instead of starting right here, right? It's gonna start somewhere else. Instead of being this cosine, this perfect cosine, this is just gonna shift over left or right, right? All of that is a phase shift. It's not changing the frequency, right? And that's important, you know, for sound, right? Because we don't want it to be a different frequency if I'm standing here than if I'm standing here. That would make like recording really complicated. So anyway, yeah, it's a phase shift. And the other thing I wanted to ask you guys was, what was the other thing I wanted to ask you guys? Oh, what if I wanted to plot this, instead of time here, I wanted to see position. So I kept some fixed time, right? I don't know, x equals 1 second or t equals 1 second, doesn't matter. How would that change what that looks like? So there would be a so I think there's a shift, but there's something else too. So think about the equation, right? T, let's just call t 0 to make it easy, right? Get rid of that whole term. It's not an amplitude question. The amplitude would be the same, right? The peak would still be 0.7.
Oh.
What's left? It's not a phase thing, really. It's not an amplitude thing. Well, what else makes a signal a signal? Or makes one signal different from another? Yeah. We'd now be looking at spatial frequency, which is completely different, right? That's that number, that 5.83 radians per meter, right? So this would get stretched out. So I guess we're at 1,000 radians per second, right? So this, if we're looking at distance, this would get stretched out like all crazy and will look like a completely different frequency because it's a spatial frequency, right? Which is not what you hear, right? Because your microphone is only at one position in space, right? You don't hear that, except for that it makes, you know, acoustics what they are, and things combine constructively and destructively. But what you hear is this, right? Because you're at a fixed point, it's in space. Okay, I hope that's helpful. Sorry to digress. Mostly I just like making the animations, and it's like I can feel like I'm doing work and not do work. Okay, so let's get on to answering some questions about the actual homework. So I want to stop sharing here. Hi, everybody in the internet. And I want to share on here. Okay. Screen? Sure. Yeah. Start broadcast. Okay. So let's get to it. We got through all that. So the first question here is determine the frequency of oscillation in hertz. So we're looking at this guy right here. This is our equation for pressure as a function of position and time. Where are we going to find that bad boy? I want the frequency of oscillation in hertz. Where does that live in there? Yeah, we got to do one thing to it, right? What do we got to do? Smash it. What do you got to do? Because that's not in hertz. It's not 3,000 hertz. What's that? Oh yeah, that's an omega. Yeah, totally. Right. So what's the conversion there? Yep. And there you go. That's it. Simple as that. Cool. Now we got to define an expression describing the particle velocity u of x comma t. This is the most basic possible algebra question. I'm going to give you that equation right there, right? So pressure as a function of position and time equals c, which is our, what do we call that? Our what velocity? Yeah, the speed of sound. We call that. Can't think of that name. Anyways, right? It's the, what is it? Yeah, that's it. Propagation speed. Thank you. Propagation speed times rho zero. And we have those just right up here in the question, right? Plug those in, divide by those two things where you need to, and you're done. Cool? Easy, easy peasy. Calculate the RMS pressure amplitude. I will post this, by the way, and you'll have access to all this stuff. How do you convert a peak value to an RMS value if it's a sinusoid? Divided by root 2, okay? And what's the peak value here, if you're looking at this? What is it? Look at the original equation. 0.7, right? Because this whole argument, this e to the j and all that junk, right? At its very largest value becomes 1, right? So the peak value, the highest it's ever going to get is 0.7. That's what we're interested in. Take that 0.7, divide it by root 2, as John Woo said, and Bob's your uncle, you're done. Cool? Okay. Give you guys 1 second to catch up if you're writing stuff down. This will be posted. Using the value for part C, compute the sound pressure level in dB SPL. So dB is just, it's a ratio, right? And that's what decibels are. So you have to have some reference. In this case, we have this reference here, P ref equals 20 times 10 to the negative 6 pascals, right? This is not a power, it's a signal. So we're going to use 20 log P RMS over P ref. Now, you are using, he says use part C, but just be careful here. You need to put PRMS in there. It's not going to give you the right value. Don't use the peak there. Okay. Corey, question?
Right. Isn't that what it's calculated in hertz?
Yes, it is. Yeah. Sorry. Maybe it's just, I'm confusing you because that's a mistake I would make. Is ignore that it said in part C and just try to put the peak value in there. But you can just make sure you use the RMS. Yes, it is what it says. Yep. Now we got this Fletcher-Munson curve stuff, and we want to know approximately what
what loudness humans will perceive this to be. So we're going to get some value out of that SPL, and we need to convert it to fons. Fons is your unit here for loudness. Okay, so let's just talk a little bit about how this thing works. Okay, so the way I'm going to do this is if I'm trying to make this chart here, I am going to play a pure sine at 1,000 hertz and 40 dB SPL, right? And I'm going to say, Corey, how loud does that feel? Keep that in your head, right? And then I'm going to take a 20 hertz signal and I'm going to turn it up until you tell me it's equally loud, right? And that's what I'm going to plot here. It's like how much SPL, like what value of SPL do I need to play something back at for you to feel like it was as loud as 1K at whatever SPL. That's how you're going to build this. Though hopefully you'll do it with more than one person. I hope this is not just one person's opinion. It wouldn't be very useful. But the way you're going to use it is you are going to, let's say we're talking about 60 dB SPL at 100 hertz. Let's find that. So that looks like it's right here. So to a human, that's going to sound like 50 fons, right? Because it's on that 50 fons line. Does that feel okay? Yeah, okay. Perfect. Okay, compute the sound intensity level in dB relative 10 to the -12. This is, again, just a dB. We need a magnitude, an intensity magnitude before we can calculate a dB, and there's your equation right there. So take that pressure RMS and square it and divide it by C times rho naught, and that'll give you that magnitude. Take that magnitude and turn it into a decibel level. In intensity in decibels by dividing it by I naught. Where's our I naught? We have value. Oh yeah, it's this, right? My fault. Right, that's our I naught. Put that underneath 10 log of that ratio. I'll get you there. This is a power. We already have a square in there. It's right here, and that's why it doesn't need to be 20, right? It's already been squared, right? So it's 10 log instead of 20 log, right? Because that square is just going to jump out in there and become 20 if it was left in here. Cool. Okay, I should probably get rid of that because if you're trying to read this later and it's all drawn on top of. Anybody in the internet have questions? You guys can all still hear me. You're all still good? Yeah. Okay. Oh, thank you. Okay. Any questions on question one? That gets us through question one. It's one of these like super high school physicsy questions where it's like know the equations and know how to do algebra. You know what I mean? Right? Like there's not it's not like a ton of thinking, right? If you find yourself thinking very hard on part one, slow down. Don't thinking is your enemy always. Okay, any questions? Sweet. Let's talk about spherical waves. A spherical wave is propagating in air at a frequency of 140 hertz. Determine the magnitude and phase of the acoustic impedance at radius 1.25 meters from the origin. Here is a reprint from your notes of the equation for impedance of a spherical wave as a function of K and R, where K is the spatial frequency or the wave number and R is the distance from the origin. And that is right here for you to reference as you need. Okay, so what do we need to know? So we don't have to do any work. We know all those values, right? We know K and R, or we can find K. K is pretty easy to find, right? And we know R, and we know C, and we know rho naught, and we can just put that all in there, okay? Now, when I go to find my magnitude, right? It's root a squared plus b squared, where I'm talking about a complex number, right? The a and b from a complex number. This is totally doable by hand. What you would do is you would take this complex number that you're that you found by plugging in the values in that equation for z. You would multiply the top and the bottom by the complex conjugate and to get a simplified complex number, and then you'd take a magnitude this way, and then you'd take an angle by taking the arctan of b over a. Make sure when you do that, whenever you use an arctan, you know what quadrant you're in, right? Because it will get you, you can be 90 degrees off or whatever very easily, right? You can also just use the Matlab function absolute value and angle, right? You don't have to do any complex conjugate stuff. It'll do that for you. You don't have to do anything. You don't have to know what angle you're in. Those are those two functions that'll get you there. Cool. And as always, I recommend doing it that way just to check your work if you are doing it by hand. I always do, for sure. Okay. Any questions on that? Plug and chug, right? We're still in high school physics here. Yeah, okay. Show in general, this is part B, show in general, the magnitude of the impedance for a spherical wave reduces to the specific acoustic impedance when the listening point is many wavelengths away from the original plane wave equation. So here's what you need to know. The equation for Z, you need to know that Z naught equals C times rho naught, where Z naught is the specific acoustic impedance. So we want to see that this thing here reduces to this thing here, right? That's what we're trying to show, okay? If R is much, much larger than, what is that, gamma? Gamma, right? Gamma, lambda, that's lambda. Anyways, okay, so that's what we need to show. K has this relationship to wavelengths, right? It's just K equals 1 over wavelength, right? So you need to know that too. And then this is another one of those things. If you turn in 2 pages of math for this, don't do that, right? This is 2 logical lines here, 3 logical lines. Start with the sentence, if R is much, much greater than, what did I decide that was? Lambda, right? Then what? Then what happens? Something goes to 0, right? Probably. Yeah, you can bet. There's not much here. This is not something you want to think about super heavily, right? Even if you're not used to doing these sort of problems where you have to show something, this is the simplest possible version of that, right? I mean, if you want to be, super official, you can talk about what happens in the limit, right? But you can also say, if R is much, much greater than lambda, then blank equals 0. And do, a little bit of these squarely equals, right? Guys feel okay about that? Totally. Further than that? Yeah. Yeah, I mean, this is the thinkiest part of the whole thing, but don't think too hard about B either. Like, it's pretty darn straightforward, I think. And that gets you 2/3 of the way through your homework, and we're going to talk about 3 next time. Questions, thoughts, and concerns?
Yeah, I had a question back
Yeah.
with the equation for Z.
Yeah.
What was R again?
R is the distance from the origin, which is just this radius right here. Good question.
Oh, okay, thank you.
Yeah, you're welcome.
This is due this coming next Tuesday.
Right, so we will have one more recitation before it's due.
It's just funny, I think on the PDF, it says Friday.
Oh.
That's not a real day.
It's like not an actual, like,
Friday the 29th.
yeah,
Not a day,
Tuesday, I'm almost sure.
something like that. Okay.
That's probably left over from a previous year, I'm guessing.
Right.
Any other questions from internet people or real life people? No judgments about, the relative quality either. No? You guys are good? Okay. I think, I have chat. Hold up. What's R again? Oh yeah, we got that. Okay, cool. Yep, R is just the distance. All right, I think that's it. Does anybody on the internet have like specific questions about their homework? You got an answer and you're not sure about it or anything like that? I gotta. Relative, so it should be watts per meter squared, right? Because that's what it's relative to. Yeah. Yeah. No, the internet's good to go. Okay, I think I'm gonna end the Zoom at least. You guys have a wonderful day. I'll see you next Tuesday or Monday, sorry.